So what the hell is going on this beautiful figure over here? So still for our example system, and the equilibrium conversion line shown here where the rate goes to 0. What is now also populated on this figure is some iso rate lines. So lines where the combination of concentration and temperature is such that as I follow this line, I will achieve the same rate. So per illustration, if the rate is at 10% conversion, that concentration and a temperature of 120, I can achieve a rate of 500 moles per kilogram per minute. If I want to achieve that same rate when my conversion is 30%, I have to operate my reactor at about 155 degrees Celsius. So similarly, all of these iso rate lines were collected and constructed. I will not expect you to generate a figure like this, but it's used for illustration purposes on how to think about designing reactors with equilibrium reactions, specifically exothermic equilibrium reactions. Easy to see here is that at a low conversion, when I still have a high concentration of my reactant A in the line, I will have higher rates, and that's especially true when I have high temperatures as well as high concentrations of my reactant in my mixture, so low conversion. Where the temperature becomes low and where I have high conversion, so I've got lots of my reverse reactant that can participate in the reverse reaction, I achieve the lower rates. What you should notice here at the rate goes to 0 line is that all the rates kind of are bunched up. And that is where this 3D-ness of this map comes in. So if you now want to visualize this, let's just see what happens here at 10% conversion at this very high iso rate line. If I just increase the conversion by almost 4% to 14%, whoop, I am immediately at 0. So it's as if I'm at a very high cliff, but very high rate cliff, and then I can drop down via cliff face into the ocean. So bunch your eyes up and then you can see these are actually cliffs of very high rates. Similarly, if I now, for instance, look at the 500 rate line and I'm at a temperature of 160. If I just, and I keep the concentration the same, if I just increase the temperature a little bit, almost to 170, I suddenly fall off the cliff. So close to this line, everything, this is like a cliff face. And if I'm here at where the rate is almost 0, if I just moved from almost 0 to 0, this is where you are at the beach. This is like the ocean, this is like a high cliff face there, and it's falls from, you can walk from the beach, you can walk uphill to this very high cliff. The purpose of this figure is to allow us to understand what's happening with the rate along various trajectories or possible positions in a reactor. And for that purpose, we want to evaluate first isothermal conditions. If I start with X is equal to 0, keep the temperature constant, what happens? Draw a graph of how the rate will change as a function of X for a constant temperature. That's this green line over here. Then we've got our adiabatic energy balance line. So the blue line over here, as illustrated on the previous one, illustrate what happens to the rate as I increase the temperature or as I increase X. We've touched on that in the previous video. And then, of course, we've got this constant conversion line. So if I keep the concentration the same, but I increase the temperature, what is going to happen to my rate? So I challenge you to pause here to see whether you can construct these asked figures on your own before moving to the next part of this video. If I consider the isothermal case first, so changing the concentration in my reactor, reducing the concentration of forward reactants, increasing the reverse reactants, the rate parameters therefore will remain constant. What I will see happening is a decrease in the rate, and it's going to be fairly linear, except here at the point where I approach equilibrium, where my rate lines becomes bunched. So if I should draw this, I will have a decrease in the rate and then where I drop into the ocean, where I am going to go to my equilibrium conversion. So we discussed the adiabatic rate profile in the previous video, but just to confirm, I will have this initial increase in the rate. It will go to a maximum value, and then it will suddenly start to drop. So you will see that it intersects the same rate line twice. So at Ra80, it will operate at this concentration temperature combination, but I will also be able to achieve an 80 rate mole per kilogram minute at this concentration and at this temperature combination. So if I should draw that figure, once again, there will be an increase in the rate, go to a maximum, and then the drop to the zero rate where I achieve equilibrium conversion. Another very important profile to consider is what will happen to my rate if the concentration stays constant and I'm just changing the temperature. So in order to keep the concentration constant, I keep the conversion based on my inlet conditions the same. You will see an increase in the rate. 1, 2.55, 10, 20, increase, 250, and then it goes to about 500, and then 250 again, and then down the slippery slope of that cliff of ours. So for each x value, what that implies is I will have a maximum and optimum in the rate, and then the drop down the cliff to the zero rate value. So important to see that I can achieve the same rate at two different operating temperatures. Implication is that if I am I targeting a specific conversion value, there will be an optimum rate. So if I maximize my rate, I minimize the amount of catalyst or the volume of my reactor that I need to employ in order to achieve that conversion. However, if I am now tasked to convert 80% of my feed in any reactor or a reactor train of my choice, so 80%, I would be tempted to say, let's for 80% inspect my rate. That's the maximum in a rate. So let's just target a CSTR, and we design it by manipulating the energy and the mole balance to operate at that maximum in the rate. So if I just visually interpolate there, it's somewhere between 20 and 40 moles per kilogram per minute. But still, this is very close to beach level where my rate is already high. So I left all these beautiful views of the high cliffs and the very high rates that I could utilize unused, and I jump immediately to this very low value close to the beach. So it's often not a good idea to jump in a CSTR to a very high conversion value, even though you optimize at that single conversion value by targeting the maximum in the rate. In an ideal world, I would like to follow, as I increase the conversion, I would like to just remain on that highest point and then slowly work my way down until I achieve my final conversion. So if I want to express that, I would say I would like to follow the line where the rate as a function of temperature for each constant x value, where that is equal to 0. So because I want to operate there at that highest points in my rate. So how is that practically possible, and can we approximate that? One suggestion discussed by Vogler is to operate a few adiabatic CSTRs in series. So there's no heat flow to or from the reactors themselves, so they will follow, therefore, the adiabatic energy balance when we consider the change in temperature versus conversion over each of the reactors. And then we have an intercooler where no reaction takes place between the heat exchangers to reduce the inlet temperature to the next reactor so that it can climb up this hill. So we are going to, I'm just going to show you with the pointer now, start reactor 1, increase adiabatically to the conversion in reactor 1. Cool down to the inlet temperature of reactor 2, increase adiabatically to achieve conversion in reactor 2. Decrease to inlet temperature to reactor 3, and then finally go to my final requirement of the conversion that I really want to achieve. So let's say the overall conversion that was specified here was 90% based on the inlet flow rate of A. You would have to specify the inlet temperature to reactor 1 to start off your procedure. So let's just say we chose it somewhere over here. And now adiabatically we are going to operate that so that it hits that maximum in the rate somewhere there. So of course you're going to do this in Python to determine what's the maximum point of the rate on that adiabatic line to size this reactor, operating at the maximum adiabatic rate. So that will then give me the operating temperature of reactor 1 as well as the operating concentration, which is linked to the conversion in reactor 1. You now have to decide to which inlet temperature for reactor 2 you are going to cool that down. So that will be a design specification. So let's just say we are going to cool it down to, while no conversion takes place, let's say to 60 degrees Celsius. So this is now the new inlet temperature to reactor 2. So from there, once again, we follow the adiabatic line. We want to operate at that maximum somewhere there. So that will give me a conversion of 70%. That will also give me the operating temperature of reactor 2. So I have the over-based. Remember this figure, all of the conversions based on the inlet concentration or the inlet molar flow rate of component A. So now we're at that position. And I know that I must stop there on the 90% overall conversion line. So I might as well say that my last reactor must target this maximum in the rate over there. And I know the slope of my energy balance, so I can work it in reverse and say, okay, this is the slope of the energy balance. Therefore, I need to cool down to this inlet temperature. So that is now fixed. So that will not be something that I am going to specify or choose, because it's fixed based on that maximum operating rate and the adiabatic energy balance. So I now know what my inlet temperature to my third reactor must be in order to minimize the amount of catalyst that I use in each of these reactors. So although in most cases you will not be required to graphically go and I will not require you to generate a ISO rate figure like this or solve graphically in your tests, you will be able to use Python and you will have your rate equations and your energy balance parameters. It is a very good idea to understand why this happens, to have this picture in your mind as you start modeling, for instance, a reactor train like this. I will leave it up to our discussion class for you to comment on whether you, in fact, think that this is the best way to go about stepping down the hill, or maybe you can find of another way in order to utilize the vantage points of the high rates at the lower conversions as you move towards your final goal of 90% conversion.